So welcome, Professor. We are here with Professor Jaroslav Fabian from Regensburg University in Germany. We are very excited to have you here. Thank you for your time. We want to know a bit about your journey and insights on your field of spintronics. So let us start from the very beginning. What initially sparked your interest in science, and what particularly drew you to the field of physics?
Yeah, thank you very much, and thank you for hosting me and for having me for this interview. It's really exciting for me to be here. Well, I got fascinated by mathematics, by mathematical analysis. When I was in high school, we didn't have it yet in the curriculum, but I got to read about it from some books, and I was fascinated by the level of description that mathematical analysis provides for classical physics. And then I got hold of a book in our local library in Slovakia of quantum mechanics, where I read about uncertainty relations, electron-particle wave duality, measurement problem, and I was sort of hooked. I tried to understand what is it all about. I wanted to understand what reality is. So this drove me into physics, just this basic understanding of the world around us. And physics is the right profession, of course, for that, because you are not only expected to sort of ask the questions, but you're also expected to answer some of the questions. Well, that's how the journey started. It still continues. I still do not understand what the whole thing is about, but I'm still fascinated by the quantum world.
I think we all fell in love with the quantum world when we started. Now it's kind of a love-hate relationship. But more specifically, your field of expertise is spintronics. For those that may not be as familiar with it, could you give us a basic overview of what spintronic entails?
So the spintronics is about dual control of the electron charge and the electron spin. So in conventional electronics, we control the flow of electrons. So this is what we call electrical current. Now, electrons also have a spin, and this is a new, what we call a degree of freedom or a control knob that we can change and manipulate. And by changing and manipulating it, we can actually influence the control of the electronic charge and the output of the electronic devices. So we have this additional tool. In addition to electrical controls, we can control electron spin magnetically, optically, to change the output of the devices, and we can store information, for example, in the electron spin, because the electron spin, as a fundamental property of the electron, provides what we call non-volatility. That means the information is not really destroyed. It is kept for a reasonable time in the electron spin. So this is what the spintronics provides.
Working on spintronics certainly makes you an expert in this subject. So here comes maybe a tricky question, especially when you're an undergrad physics student. How would you, in simple terms, define the spin of a particle?
Okay, so this is the question I started with as a high school when I tried to understand quantum mechanics, and I still do not know it. We only describe the electron spin or the particle spin. We know that elementary particles, such as electrons, photons, neutrons, protons, they have some kind of an intrinsic or internal rotation that cannot be visualized in classical terms. For electrons, the electron spin is as fundamental as its charge or mass. We do still visualize it as a rotation of an electron as a ball, but we know that this is not a correct picture, and we know it from already the discovery of the spin 100 years ago, as I explained in the colloquium. So the crucial phrase is that the electron spin we can visualize as if it were a rotation, although it is not. And the reason is because the spin has similar properties to orbital momentum, or we call it angular momentum, with respect to symmetries, like mirror symmetry, rotational symmetry, and so on. So we just visualize it like this, but it's an inherently relativistic phenomenon. It appears from the Dirac equation, and it's an intrinsic quantum phenomenon, because however we measure the electron spin, we always get either plus or minus 1/2. If we have a spinning ball, like a classical ball, if it rotates more, the orbital momentum is more, and we can change it continuously. But with the electron spin, we cannot do that. Any measurement gives only two values, plus or minus 1/2. So unfortunately, I cannot really tell you what the electron spin is. I can just describe it.
Related to spins, and talking about 1/2 or plus minus 1/2, your work also delves into manipulating the spin of particles. What is the main difference, or let's say fundamental and practical differences between manipulating the spin of fermions and bosons, and is there any advantage of this or disadvantage of choosing one over the other to work with?
Well, first of all, we have two types of particles in quantum mechanics, fermions and bosons. For fermions, fermions have what we say half integer spin, 1/2, 3/2, and so on. Fermions would be electrons, neutrons, and protons. Their electron spin can be manipulated by magnetic fields, by electromagnetic fields. For example, in a magnetic field, the spin of a fermion would just precess, we say the precession of the spin, or rotates. And this can be also influenced by electromagnetic radiation, such as microwave radiation. Also, nuclear spins are important, like proton and neutron spins. Atoms or nuclei of the atoms in our bodies have spin, and this has already been used for a long time, for example, in magnetic resonance imaging, MRI, in hospitals. For us, more important is electronic spintronics, electron spintronics. Fermions are very important for stability of matter. So without fermions, all the matters would just collapse. So this is the Pauli principle that tells us that two electrons cannot sit in one place, not to be in the same state. And this is how the electrons in atoms are sort of stack up in different levels. So this is very important for the stability of matter. When we talk about bosons, bosonic particles, they have integer spins. For example, 0, 1, 2, 3, and so on. Typically, these are sort of force-mediating particles, like photons. Photons have spin 1. They mediate electromagnetic interactions between electrons, between charged particles. For example, to manipulate a photon spin is the same as manipulating its polarization. That means the electric field of the photon field. And this can be done routinely in labs by wave plates, changing from circularly polarized to linearly polarized, and so on. Circularly polarized photons, they have a specific projection of the spin.
The electron and the electron spins, one could say that they are the center of spintronics, but I believe that so are the spin interactions. Let's focus a bit on spin-orbit coupling. In your work, you explore the possibilities of changing the spin-orbit coupling in interfaces through methods like stacking, twisting, or gating. How do these specific methods affect the spin-orbit coupling? Maybe this might be a bit of a repetition with the talk you gave us before, but let's try to give a view more distended if we can. And what are the major challenges of achieving control over these parameters?
This is indeed the research that we have been pursuing for the past years, not just us, but our community. There are two major interactions in spintronics. One is so-called exchange interaction, which gives rise to magnetism in the magnetic materials. the spins of electrons are aligned, generating a strong magnetic field that we can see on refrigerator magnets, for example. The other interaction that we do not have on our refrigerators is the spin-orbit interaction. It's a little bit more technical. The origin is relativistic physics, again, the Dirac physics, but we could describe it in classical terms as the interaction or coupling or interplay between the electron spin, which is this internal rotation of a particle, and the orbital momentum of the particle, which is how the electron moves in real space. This interaction is very important because it couples the orbital degrees of freedom of the electron, such as the velocity of the electron, with the spin degrees of freedom. So for example, if the velocity of the electron is in one direction, then the spin will be pointing in one specific way. But if we reverse the velocity, for example, we reverse the current, then the spin will point another way. And this can be used to manipulate the spin electronically by passing electrical current through a strong spin-orbit material. Unfortunately, or fortunately, graphene is not a strong spin-orbit material. Graphene has a very weak spin-orbit coupling, which is good for transporting the spin, because then graphene electrons do not interact much with other degrees of freedom, and the spin can survive reasonably long. But it's not good when we would like to manipulate the spin, for example, to induce some spin precession. So for this reason, van der Waals engineering provides a pathway how to change or influence the spin-orbit properties of electrons in graphene by placing graphene on top of a material which is not really conducting. We say it's a semiconductor, but has a strong spin-orbit coupling. We can induce spin-orbit coupling into graphene. This is called the proximity effect, because graphene is in proximity with the semiconductor. Now, suddenly electrons in graphene are very happy because now they have a strong spin-orbit field, although they are still moving inside graphene. They are not really in the other material. And it turns out that in spintronics, we are able to control the magnitude of this spin-orbit interaction, or how the electron spin reacts to the changes of the orbital degrees of freedom of the electron, by van der Waals engineering, such as twisting, for example, or straining of graphene. So take twisting as an example. If graphene is stacked in such a way that it's perfectly aligned with a substrate, that means it has a zero twist angle, the lattices are pointing in parallel, then we have a very strong spin-orbit coupling, turns out. But as we rotate graphene by 30 degrees on top of this, then we go to zero. So then we can go really from large value to really zero, and anything in between we can get simply by twisting. So this is what I mean by tuning the properties of spin-orbit coupling or spin properties in graphene by van der Waals engineering. This is just one specific example.
Moving on a bit and thinking about the future, with the development of spintronics and the rise of 2D materials, which one do you think might be the most important application for spintronics in the fields of, for example, computation or data storage? And how central do you view their position when it comes to the development of quantum information systems?
Nowadays, the new or second generation of spintronic devices concerns magnetic random access memories, which are non-volatile sort of memories. Non-volatility is provided by the electron spin. So this information which is encoded in the electron spin stays for a long time, because we have a magnet and we know that the magnet polarized in a certain way stays polarized in the same way for a very, very long time, longer than charge, which is used for storage information in electronic sort of electronic memories. And spin can also be easily manipulated with less energy needed than electrical charge, because to change the spin, the electrons do not need to be sloshed from one place to another, thereby also expanding a lot of energy or needing a lot of energy. So spintronic devices do not need so much energy to be powered. Now for 2D materials, probably doesn't matter what I believe, but I think now, or I'm excited now about the prospects of applying them for magnetic random access memories. The basic principle there is so-called spin-orbit torque. So it's based on the spin-orbit interaction that we talked about. And the spin-orbit interaction in 2D materials can be precisely tailored, unlike in conventional systems. And the spin-orbit torque devices, they need tailored spin-orbit interaction. We need to know, or it will be good to know, or to control this interaction in terms of in which direction it points, what is the magnitude, to have high efficiency spin-orbit torque memories. So the basic idea, just for the audience, would be that we pass a current through a system, and this current then can lead to a flipping of magnetization. So magnetization, for example, up, storing information 1, could be flipped to down, storing information 0. So this is how we can write the information in a medium. And we simply pass a current. With conventional devices, the current densities required for that are still rather high. And we have hope that with 2D materials, this can be lowered so that our devices could be more efficient and consuming less power. So this is what I think could be the future of spintronics with 2D materials. But of course, there are many more possible applications for neuromorphic computing, or ultimately for spin-based quantum computing, where we have spins in such structures as what we call quantum dots. That means very localized. And manipulating individual spins means manipulating what we call qubits in quantum computers. And with that, we could perform quantum computation. But we still have to see how scalable such devices would be in the future.
Related to these 2D materials, which materials do you think are the most popular in spintronic applications? And specifically, which one do you think is the most, that has the most possibilities to be the future material of spintronics? And what unique properties does it offer in comparison to conventional materials nowadays?
Graphene is still the most important material there. It has a weak spin-orbit coupling, but it provides channels for the spin transport. So this is very important. So the spin has to be created somewhere. For the creation, we would need a magnetic material. There we have two-dimensional ferromagnets, two-dimensional ferromagnetic metals such as iron germanium telluride, which has nearly room temperature, Curie temperature. So it's a ferromagnet up to room temperatures. This can be used to inject the electron spin. The spin can be transported in graphene, for example. If we want to manipulate it, then we could use a proximity effect. So spin graphene together with the transition metal dichalcogenide, such as tungsten diselenide, for example. There are also materials that are stable in air, or magnetic semiconductors such as chromium sulfur bromide is very prominent nowadays. And then strong spin-orbit materials such as tungsten ditelluride. So one could imagine a combination of a ferromagnet, such as iron germanium telluride, which is a metal. Electrons can pass through it very easily. They are magnetic, but to manipulate this magnetization, one would put it on top of, let's say, tungsten ditelluride, which is another metal, but has very strong spin-orbit coupling. And then electrons in the magnet would feel the spin-orbit coupling and could, for example, flip its polarization when a current passes. The limitations that we have there are experimental, meaning that many 2D materials are very sensitive to the ambient environment. They, we say, degrade very fast, and then we have to encapsulate it, put it in between other materials to protect it from the environment. But let's say graphene, boron nitride, transition metal dichalcogenides, chromium sulfur bromide are robust, and they provide a very good basis for exploring spintronic functionalities.
Let me ask you, what do you think still needs to be overcome to make spintronic devices a widespread technology?
For 2D materials, I think the problem is the quality of the materials. We would need to create materials in large batches, let's say wafer-sized materials with high quality. Experimental physicists still believe that the best materials are so-called exfoliated materials, so with a Scotch tape technique. And you would agree that this is not really scalable for industry. You cannot imagine a million people like peeling off layer by layer and making a transistor out of it. So I think this is a big issue, and there is a lot of research in this area, the scalability of the production of high quality materials. We still need to understand a lot of basic physics of two-dimensional materials because there is such a variety of these materials and endless possibilities of their combinations for van der Waals engineering that we simply do not have research manpower to explore it all. So we do not yet know all the possibilities. We are just scratching the surface so far, and we have to dive deeper into the material science of it, also the basic physics science of it, to see what are the possibilities. So far, we are trying to extrapolate from conventional devices, from conventional functionalities, such as I mentioned, this spin orbit torques. But maybe we could build something completely unexpected and new.
As we approach the end of our interview now, let me ask you a question related with the upcoming generations of physicists. Mm-hmm. Which skill or knowledge do you believe is important for them to cultivate now that wasn't as crucial 10 or 20 years ago?
I would think that there are many skills that are important now that were not so prominent 20 years ago. But the overall most relevant thing, I believe, still is as relevant as before. So I'll start with that. And this is the physics insight. So this is the most important skill that we need to have, and we need to develop you, younger generation, need to develop during your studies and your bachelor and master works and the PhD to really gain deep insight into specific system-specific problems to make new discoveries and find new applications. Beyond that, there are skills that are emerging as the society is changing. The skills are sometimes called soft skills, but I don't think these are soft, these are really foundational skills that younger generation of scientists should have or should develop. Of course, computer literacy is absolutely essential nowadays. Then there are skills that are influenced by industrial and societal needs, more collaboration, more synergies. And I'm quite excited about how science is developing into this network of interconnecting hubs among different laboratories around the world, in Europe in particular. And this brings new types of skills required from professional physicists, such as project management skills. So these are really managerial skills that set up a project, how to organize a project, and the ability to deal with modular work in science. And of course, then there are sort of, it's not really the skills, but it's a mindset that to be aligned with what the society expects from us, working towards sustainable future technologies, and not the least ethical problems of science. So with data, with creation of data, how to deal with that, and how to apply the exploration of data in ethical and creation of data in ethical way. So we have to learn all of those. So it's not easy for a generation of early career researchers, but I think these are really essential skills nowadays.
That will probably keep us on our feet. So
Yes.
with this, we put an end to our chat. Thank you very much again for being here and for taking the time to discuss all these questions with me. It was a pleasure having you.
Thank you very much for inviting me here for this lovely interview. It was also a pleasure.